So welcome to attend my fourth lecture on the chapter 4 regarding electromagnetic waves. And today on this very lecture I will be speaking about the radiation pressure and momentum of the electromagnetic field. So I will start by just giving a few minute motivation into these topics. Even though they are not the core content of this course, I would still like to point to you that these are in fact quite interesting and relevant properties of light, depending when we find a proper application where they actually matter. So these kind of regimes where radiation pressure and the momentum of EM field actually matters, I could come up with two very good and different application regimes. And the other one would be a so-called optical tweezers, and these optical tweezers and kind of forming optical traps for particles to be trapped inside. They got their Nobel Prize in 2018. So mainly Arthur Ashkin was the pioneer of optical tweezers. So that these techniques that I will be speaking about, actually they do matter quite a bit, especially in the field of biophotonics. So essentially what happens in that field, and Arthur Ashkin was the first one to realize that this actually works in practice, is that if you focus a laser beam tightly using a high numerical aperture and objective lens, at the focus of your laser beam, huge optical gradients of the fields will be formed, and these in fact can be used to trap particles inside. Especially even like dielectric particles can be trapped, but also metallic particles can be trapped when you properly adjust your field profile. But mostly the application is on dielectric particles. So one could, for example, imagine that I would have individual cells and I would want to study their properties. And individual cells, the sizes of course vary, but the range of the orders of microns might be a little bit less, might be a few tens of microns, but in any case, somewhat quite small objects. And if I would want to, for example, understand what are their mechanical properties, that I could try to imagine, for example, trying to do experiments where I'm trying to kind of see how flexible the cell is. And this, in fact, really can be related to the kind of liveliness, the healthiness of cells, that it would be pretty hard to try to imagine normal tweezers, like physical mechanical tweezers and pliers, that we would be operating on this kind of spatial scale. We're speaking of micron-sized objects. But when we are focusing a light beam, a laser beam, into a small diffraction limited spot, we're speaking about a laser spot that is of the order of a few hundreds of nanometers in size. And with that kind of object, we could more easily imagine that we're actually able to trap particles, even move around the particles inside your liquid environment into a different location, so that you could even move specific cells to another location. And we could also flex them around in order to look into their properties. And one can even infuse medicine inside, so that one can even just create a small hole into the cell membrane using a laser beam, and one can push medicine inside a single cell, so that lots of things have been done in the last few tens of years in the context of optical tweezers. So that's one regime where one can take use of radiation pressure and the momentum of electromagnetic field. So at the micron scale, so in liquid environments, in aqueous environments, and in the context of biophotonics. So the forces actually are quite strong in that spatial scale. So even though we're speaking about the absolute strengths of some femtonewton forces, so of course they don't sound like much, but when we have small enough particles, objects we want to move, then even femtonewton and piconewton forces are actually quite strong. Then another regime that is quite nice in terms of the applications and in the importance of momentum of electromagnetic light is that when we go into kind of more on the astronomical dimensions. So when we're thinking about our solar system and the objects that are in our solar system, for example, the planets, and more importantly, the different satellites mankind has launched into space. There, it is this momentum of the EM field that actually plays or can play a huge role. One example, or maybe I should further motivate this first, that okay, the forces are of course still small, so that we are not saying that the momentum of light somehow magically becomes stronger in outer space. Of course it doesn't, but sunshine, so that the radiation from our sun, even though it is creating quite small forces, for example, into the surfaces of satellites, the satellites are there and they remain in orbital motion for several days, weeks, months, and years, so that the time duration in which these forces have time to affect the orbital motion of satellites, it's actually quite huge. So we're not interested in doing anything in a few seconds, as we would be doing with the optical tweezers, but when we would be looking, for example, how a satellite is being affected, and if the satellite is being irradiated for several months during its propagation in space, we may actually start seeing quite dramatic changes from the expected motion. I might be remembering this story wrong, but I think one of the Voyagers, I don't think that we have that many other objects that we have sent into the space, of course not counting USS Starship Enterprise. Maybe it was Voyager 2 or 1, I don't remember which one, but for some time during its propagation out towards the deep space, people were perplexed that the trajectory of the Voyager seemed strange. I might be remembering the object wrong. It might not be a Voyager, but I remember definitely it was some of these objects mankind sent into outer space towards deep space region, that the motion seemed strange. And there didn't seem to be any kind of like existing explanations that could have explained this. And people were for a while thinking that are we now seeing some new physics being in place? So, for example, is it such that somehow the laws of gravity would not be working anymore as such as we would understand them to work? Or do we have some kind of dark objects nearby the solar system that is being changing the motion of the satellite? But it turned out to be the case that in fact there was no new physics, but rather just old physics in disguise, so that the satellite was being warmed by solar irradiation, and due to the geometry and the structure of the satellite, this heat that was being accumulated, it was being radiated out from the satellite into a slightly different direction, and because of this, the thermal radiation pushed the satellite into a slightly different trajectory than people would have figured that it should take. So essentially, sun was warming the satellite, and because of the satellite being warming up, of course, it had to somehow at some point also radiate this thermal energy out. And due to the structure of the satellite, the thermal radiation was not asymmetric, and that was giving a slight nudge for the satellite into a strange direction. So this was one example out of the history of mankind. Another more recent example I would like to still point out is a so-called Project Breakthrough Starshot, where the idea is and this has been funded, it's a huge project with many research groups involved and companies and foundations involved along the globe. One of the main funders is Mark Zuckerberg from Facebook, or Meta, and the idea there in this Breakthrough Starshot initiative is that could we launch spacecrafts as a mankind into a nearby star system. So Alpha Centauri, I guess, is in practice the first target that has been came up with. And the idea is that, okay, of course, the distance between the solar system and the nearest star is around 4 light years. It's a huge distance. So in fact, the idea is that there may be a spacecraft could be accelerated towards relativistic velocities. So let's say like a 10, 20, 30% of the speed of light by using laser beams. And this, of course, sounds entirely like a science fiction, that how on Earth one could be able to accelerate spacecraft into such kind of velocities. With light, like doesn't it explode? That kind of huge laser beam, doesn't it explode your spacecraft? But the point is that if you make your spacecraft small enough and lightweight enough, then you actually don't need that much of a push anymore, so that you could actually start accelerating. And that exactly is the idea. So that the idea is to come up of making a solar sail. I believe currently the best candidate is some kind of silicon nitride, if I remember it correctly. There's in California a huge group working on solving these issues. That if you make a solar sail lightweight, and then if you shine huge laser beams into this solar sail, due to the fact that the electromagnetic field has a momentum, you would be able to push the solar sail and thus the spacecraft into motion. And in fact, the idea is that you would be able to accelerate this kind of spacecraft into relativistic velocities. And then if you have a satellite that weighs, let's say, 10 grams, and it has a camera inside, then a nuclear powered camera. So then when the satellite goes and reaches Alpha Centauri, then the camera can take pictures, video, and then send this information back into our solar system. And of course, that EM radiation travels at the speed of light. So in a few years, 4 years, we would have that kind of information of a concrete pictures taking out of a solar system that is not our own. And that is the kind of main thing behind breakthrough Starshot. So can we do this let's say in a time frame of 30 or 40 years of traveling time? And I think that's quite mind-boggling that these kind of ideas actually do exist, and I think it's quite cool. So if you're interested, please Google around and have a more thorough read on this initiative. But lots of interesting stuff is taking place in that front right now. And of course, there's even more older examples, like not this breakthrough Starshot, but you can of course use a concept of solar sail, and that has been demonstrated. I think Icarus, was it a Japanese satellite that was being guided around the solar system by basically just taking use of the solar radiation into its solar sail. So these ideas definitely they work on the kind of macroscopic scale, because there the time interval of interest is not on of the order of few seconds or minutes or hours, but rather on the days, months, and years. And that's the kind of main difference that you should be aware. So on a very small scale, objects are lightweight, and you can focus light into a very small scale. So there also the forces are quite huge. You can do things on a kind of second scale, time, speed, and then on the other hand, thinking about the kind of macroscopic scale, solar system scale, even though objects are very massive, it is the forces that are being created, so that the momentum that is being created, for example, by the solar irradiation, it persists for a long time. So gradually, quite huge effects can build up in the physical systems. So this is my motivation. We don't deal with these kind of examples much in our course, but I felt that this is something we all should be aware of when we are looking into the radiation pressure and the momentum of electromagnetic field, where it's actually being applied. And I've now shown you a few examples that it's actually being applied in quite a few of scenarios, so that it really is not it's actually quite relevant. That's what I wanted to say. So let's now get started. So I will start my lecture. So in addition to the earlier properties we have discovered for the EM field, we also know that the EM field can be associated with a momentum. And this is the same kind of quantity that we know a momentum is associated, for example, with tennis balls or a earth moving around and all these objects of matter. And it was already Maxwell who predicted that when we have an electromagnetic field incident on a particle, it will cause a radiation pressure into this object. And what is the strength of this pressure? It's essentially equal to the energy density that is associated with the field. And luckily for us, we just in the previous lecture, we have calculated what is the energy density associated with the EM field. So we know now our ways of calculating what is the radiation pressure. So the pressure equals to the energy density associated with the field, and this equals to the amplitude of the pointing vector, so S, so that's the irradiance divided by the speed of light. And this is essentially like a way how we could calculate that into which direction the momentum would push our object. And this is, of course, recall the Lorentz force, F equals QE plus Q times V and the cross product with the B. This is what is being applied also for particles that are not charged. So of course, please remember that if you have a charged particle, like the electromagnetic fields, of course, do change the trajectory of that charged particle quite dramatically by just applying Lorentz force. But this radiation pressure and the momentum of light that pushes particles also applies to non-charged particles. So for example, such as cells or satellites. They don't need to be charged. Due to the rapid temporal oscillation of the EM field, we just discovered that the pointing vector also oscillates the cosine squared like time dependence it has. So what we should do here, we should also look into the time average of this pressure. And this we can readily calculate, and this will be the irradiance divided by the speed of light. So this is actually way smarter of quantity. But we do know that this radiation pressure that is being impinging on the particle, in principle, it also fluctuates of the order at the same speeds roughly as the oscillation of light. Quite interesting, but quite strange also that if we would be able to measure the kind of changes in the momentum because of this, we would see that there would be some kind of fluctuations there too, oscillations. And because the effect caused by the electromagnetic field, so this momentum, it impinges, transfers into your object, we can interpret this to be similar to a pressure, just like in classical terms. And now we can quite easily find a description for the momentum of the field. Or of course, it's a field density. It's a field quantity that we are describing. So it's actually better to describe momentum using momentum density. So that how much of momentum we are carrying per unit volume. So that then it's more easily to deal with the field quantities. So we start by considering a plane wave as always, and we imagine here that this plane wave is fully absorbed into the incident object as shown in the figure on the bottom right of my slide. So very similar to the picture that we showed in the earlier lecture regarding the pointing vector and the irradiance. And here what we are thinking is that we want to calculate of what kind of pressure we cause into this object that has the cross-section of A. And we can recall the classical mechanics, the laws of Newton, so that we can look into the F equals ma equation, as we know from classical mechanics. And we can change the acceleration to be a time derivative of velocity. And now, of course, we can change this to be a time derivative of momentum p. So of course, this is all what we know. Impulse equals to the force. The momentum can be written as sorry, not impulse, but kind of like what was I thinking here? Impulse caused by a field into an object is the force times time. So this is what I was thinking here. So that that's what I was having in mind. But let's not be sidetracked. So the momentum P can of course be written using this by a form that we have F divided by A. So that this is the classical way of describing a momentum variable parameter, so that we know that the unit Pascal is essentially newtons per square meter. So we know that P equals F divided by A. And from here we can solve with respect to F, so that we have P equals A. And now looking at the earlier equation, we can equate that this is P divided by T. By just equating that, okay, since we have the time derivative here, we can equate that here. If we are dealing with the densities, this will be perfectly fine. So we have this equation, and here T is time during which the plane wave propagates through the volume A times L. So that's the volume V, and the time T, that is basically what defines the time, is that we think that the object has a length of L. So that that's the way how do we define what is the time interval. So that T equals L divided by C. And this equation, what we see here on the top slide, like we can write it using the momentum density PV, and then the PA term can be written as the P divided by T, and then the total pressure P can be written using the momentum density, so that the momentum density per unit V, the total momentum is the momentum density multiplied with the volume. And now we can write the volume as A times L, and then of course T, the time can be written as L divided by C. And from here we can solve that the total the pressure equals to the momentum density times C. So this is now that we see that the pressure can be seen pressure caused by the electromagnetic field. We can see that we can relate that with the momentum density. And now our interest is that how we could calculate this momentum density. And from the earlier equation for the radiation pressure, so we calculated the time average of the radiation pressure P, that was equal to the I divided by C. We can look into the equation, and we see that the momentum density PV now is in fact the irradiance divided by the speed of light squared. So this is the final equation that we solved. So here, since we have this equality and we have this equality, we equate them together, and we see that the momentum density PV must be irradiance divided by the speed of light squared. And then this is the strength. And even though it's not much, but since of course we can focus light into a smaller spot, we can increase the momentum density quite dramatically. And this is essentially what is being done when we are doing optical tweezing, and when we are trapping particles, small particles, into motion or are moving them around. And this is the way that we can even impinge cause forces that are of the order of piconewtons and femtonewtons into a small objects. And that's actually quite nice, because it gives us tools to measure a lot of things on that kind of small scale. Like a lot of things can actually be discovered. For example, in terms of bacterial organisms, that how they, for example, swim around and what kind of forces they can create. These kind of things can be now measured quite accurately by just using light. So one could, for example, just see that the bacterial is propagating, swimming inside a liquid, and one can trap that kind of bacterial, and one can then kind of see that how much of trapping forces one should impinge into the bacteria, that it doesn't swim around anymore, but remain stationary. And then one can actually characterize that how strongly, what kind of forces the bacteria can be creating to be creating the motion of moving around. So a lot of very, very specific information that otherwise is very hard to measure can now be done using light. That's quite cool. And a Nobel Prize in Physics was being awarded a few years backwards on this, so that also maybe is an indicator that these techniques are actually of profound and utmost importance in many, many fields. So I thank you for following me this lecture all the way through. I hope it was a nice lecture to follow. And next, I will speak a little bit about dipole radiation. So maybe the name of that chapter and lecture is a little bit of a misnomer. Maybe I should also say EM sources and dipole radiation, so that's a lecture where we'll be speaking a little bit more about the kind of origins of radiation. Because most of the time in the course, we're only interested in propagation of EM field and what it does for matter. But originally, that EM field must have also originated from somewhere. So we should also be familiar with the kind of main sources that we can use to create light and electromagnetic radiation. But more on that in the next lecture. So I thank your time and interest, and please stay tuned in our lectures and courses. Like lots of good stuff will be on the way also. Thanks and bye-bye.